Morning, everyone. We'll just be a minute or two. We're just waiting on our first project speakers to join. Right, I can see Caroline, David. Happy to make a start whenever you're ready, David, Tom. I think if we've got connectivity issues on the animation, feel free just to skip it. Yeah, let's sorry, folks, it looks like we're experiencing a few connectivity issues. You know, as always, sort of it's a live show. What can we say? Sometimes things don't go according to plan. So look, we'll skip out the animation and just get straight into it. Okay, with everyone. David, if you just want to, thanks very much. So hello, everyone, and thank you very much for joining us for what promises to be an insightful set of show and tells covering the SIF Discovery, Data and Digitalisation Challenge project. My name is Matt Hastings, and I'm the Deputy Director for the Ofgem Strategic Innovation Fund from Innovate UK. And I'd like to start by sending a huge thanks to all of the participating energy networks, especially the innovation teams and their third-party partners who have put in a huge amount of graft during the last couple of months. Now, as with any new process, it can take you out of your comfort zone at times, and there can be a few niggles and areas for improvement, but you have really embraced this new discovery mechanism head on, and for this we are hugely grateful. Now, the fund itself has a very clear vision to deliver net zero at lowest cost to consumers and to turn the UK into the Silicon Valley of energy. Whilst it's hard to say given the current external environment, we do feel we can make the UK the best place in the world to be an energy consumer and the best place in the world to be an energy entrepreneur. Supporting UK consumers and driving business growth to deliver net zero is why we're all here. Now, our mission has three major pillars: strategic alignment with other funders and other sectors, delivering fully and agile, both the challenges as well as the discovery alpha beta mechanism, but also the way that the SIF team operates together as a unit. And critically, to focus on business as usual and commercialization. We're trying to discover the new products and services of the future that will benefit consumers, drive down costs and reduce emissions. Consumers, planet, business. This is the purpose of the fund. Now, we're on a giant leap together towards decarbonisation, and none of us have a monopoly on great ideas. So working together across the sector is how we will succeed. And our giant leap together has four key phases: challenge setting, and you will have seen we recently released our round 2 challenges for launch in September, followed by targeted ideation, where we point great ideas at great networks. The third phase, incubation, where networks can build their award-winning consortia, and the fourth phase, acceleration, where the challenge is open and we will join the ENA, Ofgem, and networks, as well as others, in hosting the first ever UK Energy Innovation Summit on the 28th and 29th of September in Glasgow. Now, the round 1 discovery projects you're going to hear from are in acceleration. And if you talk to some of the teams who've been delivering, you'll recognise that it's been quite intense. But speed is essential here. We need to move quickly, take risks, and deliver the value consumers are looking for as fast as humanly possible. And let's talk a little bit about the F word, failure. Some of these discovery projects will have failed, and that's not a dirty word. That's the very nature of discovery. These should not be judged negatively. Quite the opposite. A positive failure to us equals a quick learning. It equals a faster route to find the best solution. Instead of just fail fast, we prefer learn fast. And this again is a key aim of the fund. Finally, I just wanted to thank the Innovate UK team, David Richardson, Kate Jones and Manny Ravashankar on the innovation team, as well as Christine Kunik, Tom Paul and Amy Oswin on the PMO. And let's not forget Paul Whittemore on comms and Paul Padaruth on commercial. Also, a big thanks to our monitoring officers and expert panels. They've all worked incredibly hard to support the discovery phase, and without them and without our network colleagues and their third parties, there would be no fund at all. So thank you for all your hard work to get to this point, and the best is yet to come. Over to you, David.
Thank you, Matt, and good morning, everybody. I'm going to give a quick introduction to myself and the Data and Digitalisation Challenge. My name is David Richardson. I'm Head of Innovation for the Strategic Innovation Fund at Innovate UK. And this is the third session of the Data and Digitalisation Challenge workshops. It was actually the most popular theme in the round one challenges. So we've got a whole host of projects, and today we're really looking at predictive analytics and weather forecasting projects. Overall, the Data and Digitalisation Challenge was looking to deliver the next generation of user-driven digital products, services and processes. And importantly, we wanted these tools to be able to span energy networks, the wider industry and government, because we know how important it is for our data and digital tools to be able to join up and operate interoperably across the energy system. We had a number of themes which these projects had to work against. One of them was looking at data monitoring, quality of data and how it's collected and made accessible to people. The second one was really to develop the enabling digital products which support other challenges. So you'll see that some of the projects do have an outcome which is quite closely aligned with some of the other challenge areas, which are transport, heat and whole system integration. We really wanted things that would help unlock data access, interoperability, and produce meaningful and useful insights for third parties to build upon also. And then finally, we're looking to improve the efficiency, security, and resilience of our energy networks through digital approaches. So if the first project is ready, we've got a few coming up in each session. We'll be going to Nimbus first from SSEN, and then to Predict for Resilience and Eye in the Sky. If you could all please drop questions in the chat as we're moving through. And at the end of each session, we've got two this morning, we'll have a Q&A on each of the projects where we'll get everybody back in a panel format and pose a few questions to them. So with no further ado, if the Nimbus project is ready to go, could I have you join, and I'll start with your slides. Who's leading on this one?
Hi, I'm just checking, sorry, Zoe from Icebreaker. I'm just checking if our presenters have managed to log in. Perhaps might be better to move on to the next one. I'm not sure if they've managed to log in.
It's Gaia, yeah?
Yeah, I'm just trying to check with her now.
Celia's also here.
Yes, I am. Here. I'm here. Do you want me to share the presentation?
No, we'll go through the slides if you're ready. If you just let me know if you're ready to start. Celia, are you okay to start?
Yeah, I'm okay, but the first bit, the icebreaker one. So if they are happy to start, I'm happy. But the first slide's up icebreaker.
We will need to track down Gaia. She was definitely taking the first slide, and I think it would be better if she started it.
I wonder if we move on to the second presentation, perhaps, David, and then come back to this one.
Okay. So I'll be coming up to Predict for Resilience. Is the Predict for Resilience team ready?
Yep, we're here. going to share my screen now.
I'll share the slides. There's no need to. Let me just get through them.
Okay.
There we are. So
Thanks,
first
David.
up now, we've got Predict for Resilience, Ruru, Joe, Jethro, and Utian. So over to you.
Thanks, David. Good morning, everyone. So we're here to kind of present the background activities as well as the initial findings for Spain-sponsored project Predict for Resilience. David, would you mind go for the next slide, please? So overall, the context for the project is that we want to find a resilience approach to understand the uncertainties to help critical infrastructure to continue to provide essential services on which the whole society depends, and also in line with the National Infrastructure Commission's recommendation in 2020 for a resilience framework for all the national infrastructures. And in terms of the opportunities, at the moment, predicting and decision-making regarding faults come from a tacit knowledge of experienced personnel. And there is a clear opportunity for us to use a data-driven approach to fault prediction. And this would make it possible to predict weather events more accurately with longer visibility. And this will definitely help identify their impact on the network, and in order to protect the supply as well as to eventually protect the consumers. So the solution we're looking at is really to use advances in supercomputing and the numerical weather forecast, and to combine those together with novel statistical post-processing to better predict short-term adverse weather impacts and kind of resultant faults on the network. And we call this a weather fault system, and it will assist engineers to make more informed decisions based on actionable fault and risk predictions. And this will eventually leading to better preparedness against adverse weathers, and obviously improve operational efficiency. And as I mentioned before, we think this project is strategically aligned with the NIC recommendations, particularly with regards to anticipation, with efficient recovery, as well as the tool will provide functionality to help build upon lessons learned in order to adapt and transform the system. Next, please. So overall, a very quick introduction. The consortium is formed with University of Glasgow, with Arab, and also with Met Office to focus on different tasks and expertise within the network. Next slide, please. So within Arab, in Discovery, we carried out various different initial user engagement within Spain. We've spoken to the control room engineers, we've spoken to the IT services people, we've also organized a more get-together workshop to go through identify the initial user needs, and building up upon those findings, we put together a functional specification which will provide the level of details that is sufficient to guide the alpha phase development. And for the functional specifications, the technical components are mostly focused around the user interface, where the people can interact with the tool, and it's based on the needs identified, we think it should be a GIS-based system, and there's opportunities that we could build upon what Spain already has as their predictive analytics of energy, there's counter pre-application, and there's going to be a focus in the alpha stage, alpha phase as well to kind of build on that existing infrastructure. And also the core of the alpha phase is to refine and develop a prototype for the forecasting engine. And this forecast engine is the core element of this weather fault system, using statistical analysis techniques to predict network fault. And I'm sure later on our partners from University of Glasgow will give more details on this. And the other part for the system is really the data store. We want to pull together all the data, the relevant data that is centrally available, stored, weather and fault data, and that the data store should also be capable of being scaled based on the need. Oh, apologies, it's the fire alarm test. I'll just mute myself for a minute.
We can actually hear it too clearly, UTN, so I wouldn't worry too much.
Okay, thank you. Oh, yeah, so that's the data store, and we hope that there will be kind of expandability and further opportunities to build in this weather fault system. That's also a requirement for the data store to be able to kind of scaled up. Next slide, please. So within the kind of user engagement, we've engaged with end users and we build up user stories, requirement catalog. So as on the screen, you can see control room engineers, data scientists, the control room trainees, system administrators are the initial co-users for the system. And building upon the engagement, we've identified user stories and categorized them into kind of current condition, predicting condition, ongoing learning, and administration, those epics for the software application, as well as we've categorized all the requirements into 4 general categories, which are general and also technical, functional, and non-functionals, and all those being kind of packaged up in the detailed functional specification we've submitted. Next slide, please. So another main activity is really to get the benefits and cost right for the discovery phase. And we've looked at that the weather fault system can really transform the human-centric decision-making practices, and integration of the weather conditions into asset health information will kind of enable improvements in asset management and allow better asset prediction. So those are the things we think as efficiency benefits. And another thing I should mention is the overall approach would help Spain to kind of embed data-related skills in their day-to-day operation. The more quantitative benefits, we focused on those in discovery, as in the network fault caused by wind and gale. And within that, we've, upon discussions with the control room engineers, and we've identified that probably a 5% savings in related cost would be a reasonable assumption. And the overall cost benefit analysis is based on a kind of the do nothing scenario as the counterfactual. The development cost, we based that on the existing Spain's application, which is around £1 million, and the operational cost is also kind of built upon those what is currently incurring on this pre-application, which, because they have a similar kind of a functional requirement on different infrastructures, data supplies. So we assume that's a good assumption to assume the operational cost. Next slide, please. So on this slide, overall, you can say I've presented the baseline for the financial metrics. So the methodology is we take based on baseline investment required for the fault system, and the initial outlay £1 million for the application development, and the net savings, i.e. the savings in customer minute lost, less operating and maintenance cost of the system. And overall, we've calculated 3 key metrics: the benefit and cost ratio, the net present value, as well as the payback period. So another key assumption is within the cost benefit analysis, we have assumed that this application will be rolled out to all the DNOs across across the UK industry, such that everybody could benefit from this innovation. Overall, upon a 10-year assessment period, the benefit and cost ratios is around 1.76. And assuming a 3.5 discount rate, the NPV value we're looking at is around 430K. And given the baseline assumptions, we think the payback period is around 6 years to recover the initial investment. So those are the baseline assessment. And if there's any kind of questions, I've also included some sensitivity studies in the appendix, and we shall reserve that for the Q&A session. With that said, I probably would hand over to our colleague from Met Office. Joe, are you there? Just checking our partners from the. Jethro, in that case, would you want to go first? I haven't seen our partners from the Met Office.
Yeah, I think maybe I can probably summarize what the Met Office has done. I worked quite close with them. So maybe,
Sure.
David, if you click onto the next slide, I can do my best. So the Met Office. So hi, everyone. I'm Jethro Browell from the University of Glasgow. I'm not Joe Osborne. But I worked quite closely with the Met Office, and their role in the project has been providing scientific guidance on ensemble numerical weather prediction. So these are weather forecasts which don't only make a best estimate of what the weather will be in the hours and days ahead, but they also provide some indication of uncertainty, and we'll see an illustration of that shortly. So the Met Office, we're looking at existing products. So the Met Office, for example, produces forecasts like this, but so do a range of other weather centres, and they all have strengths and weaknesses. So some are better at different types of weather, different parts of the globe, and so on. So maybe if we click onto the next slide, we'll see some summary of that. Here we go. So here's a table of different ensemble weather products that were reviewed, for example. So we've got Met Office products at the top, and basically the trend is as you have a more local focus, so local in this case would be a weather model focused on Great Britain, you're able to produce forecasts at much higher spatial resolution. So the difference might be, a global model might be run at tens of kilometers grid scale, versus a local model might be 2 to 5 kilometers. And also greater temporal resolution. So for example, hourly forecasts and forecasts which are updated more frequently. So they might be updated every hour versus every 6 or 12 hours. So yeah, next slide, please. And so the Met Office did a survey of evaluations of these products, and also verification schemes. So it's not so straightforward to evaluate how well a weather forecast is doing like this because of the probabilistic element, and also because these forecasts typically require some post-processing. Oh, and here's Joe now. So maybe, hi Joe, sorry to drop you in, but would you like to pick up from this slide?
Yeah, absolutely. This looks like the second of my 3 slides. Are you happy to go back one?
Great.
Thanks, Jeffrey.
No
worries at all. So the part the Met Office worked on was looking at the state of ensemble prediction systems, and particularly thinking about the application of that to the problem at hand, to working on Scottish Power's transmission networks. So we did a literature review of the existing ensemble prediction systems with a little bit of background on what they are, talking about how a forecast consists of running a forecast model multiple times from slightly different starting conditions. And then on the basis of that review, we identified a number of candidates with strong performance over the UK domain, and they are identified in the table on the right there. Some of those are deterministic, some of those are true ensemble prediction systems, and very much covered their strengths and weaknesses and how they provide forecasts over different time horizons, spatial resolutions,
and also considered how it may be appropriate to consider the use of multiple ensemble prediction systems, either sort of individually or as a multi-model configuration. And that multi-model configuration might mean picking up on multiple ensembles, or it might mean combining some of the deterministic elements of the ensemble prediction systems with the actual ensemble forecasts themselves. So, for example, potentially combining UKV, which is the very high resolution deterministic product from the Met Office, with MoGREPS UK, which consists of an 18-member ensemble. It's a lagged ensemble run over multiple hours of a day. So we considered multiple different approaches to combining these models. Next slide, please. We then talked a lot about verification and application. So in terms of approaches here, there's multiple different ways of looking at this. In fact, it's a bit of a minefield. But first up, of course, when you're verifying your forecast, you need some sort of ground truth to compare that to. So the literature review considered sources of truth for the domain and sort of timescales we were interested here. And we settled on a combination of using both station observations over the areas of interest, and combining that with a reanalysis product in ERA 5. And then we considered a number of verification methods as well. So there was a bit of background on here talking about how the method chosen depends on the forecast type and the specificity. And also we very much considered post-processing as well. And ensemble forecasts, we know, often require post-processing because they contain errors in both statistical location and in dispersion. And we talked about multiple systems for overcoming some of these issues, and recommended, for example, the Met Office Improver system, which is something that's been rolled out over the last couple of years to improve the relevance of sort of site-specific forecasts, for example. We also considered machine learning techniques as well. Obviously, these are moving quite quickly and do have a role to play in that post-processing step to ensure that the errors in forecasts are minimized. And then by way of application as well, while there isn't so much perhaps in the sort of application of ensemble prediction to this kind of fault forecasting situation, there are relevant examples sort of in other sectors and in various other applications as well. So we covered those in the literature review that were written. And there are some concerning, as I said, operational decision making, but not specifically in the energy sector. And final slide, please. Finally, we came up with a series of recommendations. So the recommendations for exploration in the subsequent alpha phase. So one of them considering two separate ensemble prediction systems run in parallel, but with different horizon focus. So we know that of real interest is over the next sort of 3 to 5 days for Scottish Power energy networks. So for that, we would concentrate on MoGREPS UK ensemble, but also combining that with the UKV deterministic product. And then beyond 5 days to have kind of sort of sight of more kind of operational planning decisions and what might be coming up in the medium range, we recommended using the ECMWF ensemble. A second approach shown on the right hand side here is to do a more blended approach and to blend models from two centres to create one seamless probabilistic forecast over the full time horizon, and then utilising that forecast using either a risk-based threshold decision-making system or some kind of weather pattern analysis. And there's a bit more information on that in the literature review as well. And then in terms of verification, as I said, we came up with some recommendations for the ground truth, but also in terms of what should be a good approach towards early verification and post-processing. Jeffrey?
Thanks. So I'm mindful of time, David, so I'll try and be as efficient as possible. So the University of Glasgow's work split into 3 kind of key areas. First we see here was supplementing the Met Office literature review about weather products with a review of existing fault prediction capability, both in academic literature and also commercial products. So quickly to summarize, what we found was there's a modest academic and industry literature in this area, but mainly focused on modeling the relationship between weather and the occurrence of faults. not so much on predicting faults in the future using weather forecasts. But that gave us confidence that it was at least possible to model this relationship between the weather and the occurrence of faults. And there were a very small literature on fault forecasting, but this tended to focus on very short horizons, so maybe only up to a day ahead, and on quite specific use cases and on interesting concepts around how you actually interpret probabilistic forecasts in order to support decision making, which have all fed into our plan for the alpha phase. Next slide, please. The second thread of our work was to compile a sample data set. So we'd identified we wanted to use ensemble numerical weather prediction. SPEN provided us with a data set of faults. And we also had some ground truth weather. So I'm going to focus here on the ERA 5 reanalysis. And we wanted to very quickly establish whether there was sufficient information here to try and predict faults. So you can see for two regions of this SPEN patch here in the top right, we've got wind speed and direction indicated in the kind of the polar plot here, and then the size of the circles indicates the number of faults that occurred in that wind speed and direction. And you can see there's some structure here, but it's really quite noisy, and we were aware this is going to be a real challenge to predict faults based on data. But nevertheless, we were encouraged by literature review, and as you'll see, the subsequent analysis. And at the bottom, you see an illustration of an ensemble weather forecast. So just to give you a sense of what's happening here, we have 50 individual weather forecasts of the maximum wind speed in this instance. And you can see for the first few days into the forecast horizon, those 50 forecasts are quite similar. There's not a huge amount of uncertainty. But then beyond 5, 6, 7 days, the forecasts start to diverge as the atmosphere is a chaotic process, and we're limited in how well we can predict it. And by the time we get to almost 2 weeks ahead, which is the maximum range of this forecast, the 50 members of our ensemble have diverged significantly and are basically characterizing the average conditions for the time of year and not the specifics of, in this case, the late January. And we'll see how this plays out in terms of fault forecasting shortly. Next slide, please. So the final part of our initial exploratory analysis was to try and produce some fault forecasts using this kind of initial and quite limited data set. So we took our historic weather and fault data to build a model of this relationship between actual weather and faults. And then we fed into that the weather forecasts in order to produce a fault forecast. So we created features from the weather data we thought would help explain the occurrence of faults. The statistical model we used was based on extreme value theory. And as you can see in this figure on the right, where the black spikes are the number of faults, most of the time there are no faults or a very small number of faults. And then during severe weather, there can be an occurrence of a large number of faults, but the number of faults during severe weather can range from tens to hundreds. So this is really an extreme value problem. And we produce forecasts from 1 to 14 days ahead. Just to explain this figure a bit further, we're trying things out. This probably isn't what the final product's going to look like, but it was useful for our exploration. So we kind of have a traffic light system at the bottom, indicating the probability of any faults occurring. And then in the amber and red in the background, we have the probability of very large numbers of faults occurring. And as you can see, happily, there's quite a strong correlation between spikes in the probability of large number of faults in the red, and then actual large numbers of faults occurring in the black spikes. If you click on one, David, we should get a new picture. Great. So here are 1 day ahead forecasts. You can see that over the full 4 years we have data for. See, and we're doing quite well. If you click on again, David, we'll get another picture. This is now the 5 day ahead forecast, and you can see the forecast is less specific. but we're still predicting faults quite well. And if you click on one more time, Dave, we'll get another picture. Great. Now we're on the 10-day ahead forecast, and you can see the information is far less specific. It looks more like a kind of sinusoid almost, and what we're seeing here is the weather forecast is converging on climatology. So it's telling us a little bit about specific risks, but we're also seeing a large part of the signal here is just the seasonal variation in number of faults, with more in the winter and fewer in the summer. But we were quite happy overall with the performance. And here's the final slide. We've got some evaluation metrics. We don't have time to go into the detail, but high numbers are good, low numbers are bad. We can see across all the districts, the performance is fairly consistent over the first few days, and then degrading from 5 days onwards. But we still have some skill right up to 14 days ahead, which is also encouraging. And really where the benefit of ensemble numerical weather prediction is extending this range of predictability, which we've done here. And we've run over quite significantly, so apologies to the other projects. I'll leave it there, I think. Apart from looking ahead, which is quite important. Sorry, I should talk to this slide. So our main plans for Alpha are improving the forecast engine with higher resolution data, as we've heard from the Met Office. There's better data available, new data, other fault types. So we've only looked at wind faults, but we want to look at all types of fault, further testing. The tool itself, we need to develop the user interface and engage with project users. And in Alpha, we aim to develop a prototype of the back end and some sketches of the front end. And then also the commercialization plan, so engagement with multiple DNOs. As UTN already mentioned, the idea is that this product would be commercialized in such a way that it would be able to be offered as a service to all DNOs. And as part of that commercialization, we need to further refine the benefits assessment that we've seen the initial work on, and the route to market strategy. So
thanks, Jaffer. We'll jump straight into the next one, but thank you all for stepping in there. We've got a few minutes to win back, but I think we'll be able to do that by just taking a few minutes off the Q&A session. So I'm coming to the Nimbus project now. Over to you guys.
Wonderful. Thank you all for joining today. So we're here to talk about Nimbus and what we did in the discovery. Could we go to the next slide, please? So just a reminder of what we set out to achieve, or for anyone who wasn't there at the start, Nimbus set out to revolutionise data usage. So what we wanted to do is look at the way detailed meteorological data and models were used in the design and decision making of electricity assets through innovative uses of the data and predictive modelling techniques. And so what we did in the discovery phase was to develop a business-driven use case that will be demonstrated in Alpha, and we delivered against the objectives of our discovery proposal and met the SIF Innovation Challenge aims, in particular focusing on the net zero angle. So what you'll hear from today is my colleagues Vichy and Chris, who will talk you through the use case. You'll hear from Seela from SSE on the problem statement and the cost benefit analysis, and I will talk a little bit about our Alpha plans at the end as well. I'd just like to highlight before we move on that we've proposed quite a narrow use case for the Alpha proof of concept, and this is intentional in order to in order to ensure achievability. But the key thing here is that the principles, methodologies, and tools that are developed and tested in Alpha will produce guidelines for how other organisations within the whole energy sector can reuse this analysis, and how these processes and analyses can be retooled for different assets. So I'm going to pass to Seela from SSE to talk through the problem statement. And if we can move on to the next slide.
Hello, yes. So problem statement, as you know, and obviously other presentations have also covered the issue of climate change. So extreme weather events, of course, they are going to be more frequent. We need to be more reliable. Our networks needs to be prepared for that, and Nimbus is trying to address that from the asset perspective. So what we need to do is make sure we have enough information, and the information is granular enough, so we can actually apply the information to a predictive maintenance and asset replacement. The impact of over our assets, as you know, it's completely at the minute. We don't have enough information. Climate change, it's not it will be a reality, but we don't know how this is going to be applied in practice. And so what we need to do is use this information for moving forward for our asset investment. What we need to do as well is make sure that consumer costs are reduced, and that is by extending the life of our assets. What we need to do is ensure that we replace assets when we need to, instead of replacing them early, and only in spending money to reinforce our assets based on risk, and not just based on just, you know, as we use now, just on generic planned maintenance. We also want to do is, we also want to minimize costs from in unnecessary interventions. So let's only invest where we need to. Let's only replace when we need to. The other thing we need to do, of course, is improve the network reliability, and what we need to, and this is by reducing the total failure of events where the supply of customers is compromised. And I'll pass you on to my next colleague. So next slide, please.
Thanks, Sarah. Good morning, everyone. I'm Vichy. I'm a researcher on the Nimbus project, and I'm going to talk to you about the priority use case that we have chosen for Alpha and how we got there. So this slide speaks about the priority use case, which is modeling the effects of weather-related degradation to the probability of failure in common network asset risk models, which I'm sure quite a lot of you are familiar with, for high voltage transmission line infrastructure assets, such as towers, fittings, and power lines. Next slide, please. So how did we get to this use case? We started with research and discussions with a wide variety of shareholders, so that's academics, service providers, and of course DNOs and transmission operators, to get to a long list of 38 use case ideas, from which we then held a workshop with our SSE distribution and transmission stakeholders on the project, along with the Met Office as well. We used this use case workshop to agree on a prioritization criteria and come to a final 3 use cases, which would be sufficiently novel, specific, impactful, and works within the timeframes of the SIF programs as well. So through this use case workshop, 3 finalists, which are here on this slide, which broadly cover historic data, asset risk modeling, and the third one being real-time weather monitoring. Next slide, please. So after the workshop, we then had our work cut out for us, where we deep dove into these 3 priority final 3 use cases. We also wanted to understand the specific problems, the data availability, and the impact to the wider stakeholders in the energy system. So through further 2nd round, 3rd round interviews with DNOs, transmission operators, academics, and service providers, we came to the realization that a wide variety of these people who we spoke to considers that the meteorological input into the common network asset risk models, so CNAME, NARA, and NAM, which are currently on this slide, are insufficient in considering the weather or meteorological impacts onto the asset models. And these have been described as insufficient and at a basic level for the lifetime of the assets and the models that are being used to manage them. This led us to further focus down the use case, looking at data availability, undertaking a literature review, and we spoke to both transmission and distribution teams to understand the needs and criticality between 3 use cases. This led us to then also try and understand specific network assets that we could use as a proof of concept. Next slide, please. with SSE, we isolated a specific network asset, which we would be using as proof of concept. This is a Digitalisation transmission line. It covers around 200 towers running about 60 kilometers from north to south of Scotland, chosen because it traverses a diverse terrain and experiences a combination of weather conditions. But more importantly, it has a rich maintenance and service history as well, going back a decade or more. And this looked like a sufficient amount of data that we could really do some justice to the use case. We identified through our research gaps in asset management methodologies. So specifically around gaps in asset degradation information. So looking at the whole lifetime of the asset as opposed to just when asset failures occur. We wanted to also consider general weather impacts over time as opposed to just extreme weather events that tie into the asset risk considerations. And finally, we wanted to look at the degradation of the asset systems as a whole, as opposed to only specific components like bolts and the material. So now I shall pass on to my colleague Chris to talk to you about how we are actually going to find the data to make this use case possible. Thank you.
Thanks very much, Fushi. My name is Chris. I'm another researcher at Icebreaker One. There are a number of internal data sets that are likely to form inputs into this use case. First of all is the asset registry and risk reports. And these are fed by condition reports from visual inspections by drones and helicopters and in-person visits. And these already form part of the network asset risk metrics reporting. We also require the location and elevation of towers and the routing of the lines. And this information is already in SSE's GIS system. The last category of data is maintenance history, and it hasn't previously featured in risk reporting, as Fuchi explained. So the use of this information in proof of probability of failure calculations will be innovative. For the meteorological data, there is quite a bewildering range of potential data sets. So to help focus our assessment, we established requirements for candidate data sets. So firstly, due to the long lifetime of these network assets, we need more than 10 years of data in the meteorological data set in order to track deterioration and map it to the weather that's been experienced by the asset. Secondly, we need quite a wide array of weather factors to ensure a thorough analysis, but specifically the data must include wind strength, direction and temperature ranges. And then finally, we set ranges for spatial and temporal resolution to enable the analysis to differentiate conditions experienced along a relatively, on meteorological terms, relatively small 60 kilometers of line that we have chosen for the focus for the proof of concept. So from this, we identified 3 candidate data sets: HAD UK Grid, ERA 5 and EURRA. However, none of them meet all the requirements, so it's quite likely that some combination of them will be required for the analysis. Next slide, please. So a key part of Icebreaker One's brief, alongside looking at the data, was to assess the interoperability and the broader applicability of the data to the use case. So on the input side, we're expecting some hands-on experimentation will be required to find the optimum approach to connecting and analysing the asset registries, the GIS information, the maintenance history and the meteorological data. This will be undertaken in the alpha phase. And because the industry uses a common framework for reporting asset risks, we hope that the process, models and parameters we will establish in the alpha phase will be readily transferable to other assets and to other industry players, both in electricity transmission and potentially wider sectors such as gas, transport and the built environment. The mobilisation of weather, asset and risk data required to implement Nimbus throughout the industry will also require a shared, well understood and comprehensive approach to data governance. This we will also develop in the alpha phase of the project. I'll now hand over to Saila to share SSE's cost-benefit analysis for the use case.
Yeah, so for the CBA, we use the Ofgem Rio T2 template, cost-benefit analysis. The template used the average T1 costings and estimated Nimbus benefits. In the CBA, we assumed a full Rio T2 refurbishment intervention on the overhead line, which is Bewley, and then modeled the whole life costing under 2 separate scenarios. So this is the first scenario. The first scenario includes inspection and condition assessments are undertaken in line with current policies and modeling capabilities. In this scenario, what we have is inspection and condition assessment of the whole overhead line across the lifetime of the asset. Fittings only replacement after 20 years of the whole circuit. Fault repair once during the lifetime of the asset, and full overhead line refurbishment of towers and replacement of fittings and conductors after 40 years. The next scenario is on the next slide. So we can move one slide. Okay. That scenario includes the enhanced predictive modeling from Nimbus, which over time will influence changes to lifetime intervention policies. And that in this scenario, we included inspection and condition assessment of the whole overhead line across the lifetime of the asset with 5-year reviews, resulting in a risk-based approach that reduces the annual cost over the lifetime of the asset. Fittings only replacement after 15 years and 30 years. It's a targeted replacement of the highest wear fittings only. Full repairs, cost avoided, because obviously we moved to a cost, a risk-based intervention replacement. Targeted refurbishment of towers and replacement of fittings and conductors after only 40 years. And based on this case and using the 2018-2019 costings, this assessment shows a net NPV reduction of 4.5%, which is compared to the baseline approach. As you can see, so this is a significant benefit. This NPV reduction is significantly increased when the original capital cost of the assets are excluded from the calculation. And that's what we covered in this cost benefit analysis. The next slide, please.
Thank you very much. So before we wrap up, I just wanted to talk about Alpha, where we've broken down the work into 6 work packages. So the aim for Alpha is to work on the proof of concept and data accessibility and standards for interoperability. So the work is split across 6 work packages. Work package 1, which focuses on project management, is quite self-explanatory. So it's successful delivery of the project to time and budget. Work package 2 is the proof of concept for the Bewley to Shin line, which will be showing Nimbus in action, in particular in SSE's context. Work package 3 focuses on documenting the benefits, challenges, and key lessons from that process. And work package 4 is we've named data accessibility. Its key outcomes will focus on identifying additional data sources and data sets to improve risk modeling and management at an individual asset level, and wherever possible, increasing the accessibility of this data by adding it to open energy. Work package 5, we've named standards for interoperability and data sensitivity. And what we'd be doing there is supporting the energy industry to apply Nimbus, and helping organizations across the energy industry understand how they can better classify and share data, including in implementing the Energy Data Task Force presumed open principles and also the open energy data sensitivity classes. And then work package 6 is understanding the benefits to SSE and the consumer. So it's taking the cost benefit analysis that Sailor's just talked through and taking it to a further level of detail. And so that's it from us and the Nimbus team today. Thank you very much, and I look forward to your questions.
Thank you very much. We've just got one more presentation before we move on to the Q&A session. So I'll come to the Eye in the Sky team if you're ready. I'll just have to skip through all of these. And the Eye in the Sky project is looking at using satellite data for better faults and resilience forecasting. Over to you. Have we got the Eye in the Sky team? Anybody? Tom, you can just check who the presenters are for me, could you?
The presenters should be on the initial slide, are they not?
Alex.
Alex is here. Well, he was.
Again, maybe just move on to the next one, David, if the speakers, I suspect there's been some connectivity issues along the way, perhaps.
This is the final presentation in this session, so...
Okay.
Wait, if we could have everybody back in and we'll just do a short Q&A session for the two projects we've just had. If there are any more questions, please share them in the chat box as well. And we'll spend a bit of time going through these and hopefully the Eye in the Sky team. Tom, if you could just drop Alex the message, that'd be great.
Already done.
So we've got a question from Matthew for the Predictive Resilience project, which is, was this trialled on the recent storms like Storm Arwen? And if so, what were the results? And I think actually this was developed a little after, but maybe you could comment on how it might have been used in those sorts of situations as well.
Yeah, I can maybe start on that. So we haven't looked at Arwen specifically, though. The results I showed were based on evaluation on all the faults that have happened in the past 4 years, so from 2018 to around mid-2021. And we've been satisfied that the performance in that we believe with improvements it will be valuable. But the question highlights a really important issue, which is of course the forecast itself doesn't add value unless it enables users to make better decisions, and that's really something that will be key in Alpha. You know, our user engagement, making sure that forecasts are communicated in a way that they can be consumed effectively, and also in such a way that they fit within existing processes, so that better decisions can be made. On Arwen in particular, I've looked at it in a separate project, and I think it's quite a good example because Arwen was actually predicted relatively well several days ahead. I see Joe nodding, which is encouraging. But again, predicting the decisions we're hoping to inform are things like making sure human resources and other equipment are available where they're going to be needed in order to respond to major events like Arwen. We're not going to be able to prevent these faults happening in the vast majority of cases.
And who are the primary customers for that advice then within the network itself? Do you have particular business units that you need to get these messages to?
Yeah, so within SPEN, it's the control room. So they're responsible for coordinating what's happening on their network. So that includes, you know, planned maintenance and also dispatching teams for reactive maintenance. And also the likes of maintenance planners who are maybe not, you know, in the control room, but will be planning maintenance over the days and weeks ahead. I think Etienne, do you want to add to that? You know, you identified quite a number of user groups.
I think probably just only one to add really is also the emergency response planning team as further identified in the review kind of part of the functional specification. And as Joshua mentioned, it's quite right, is how the key point is get the prediction and then communicate actionable tasks to different teams across the network.
Yeah, we also discussed whether these forecasts should be made available to other stakeholders outside the network companies, so like, you know, local authorities, for example, maybe even the general public. And that's also something I'm sure we'll revisit in Alpha in our engagement with DNOs, to what extent that will be useful, and then if so, the best way to go about that.
Absolutely. I think this came up with the user engagement we had with the IT department within Spain, and they are kind of keen to say that there's this open data initiative across the different networks, and if we can actually take advantage of this forecast. And I think, as mentioned in the very beginning of the introduction of the SIF challenges, that we want to make data available such that third parties can build upon and benefit from. So this is certainly one of the intentions we've also identified in Discovery.
We've got a question come in from Grant as well. And Grant's asking, in terms of the data inputs or outputs from the fault forecasting, is there some thought to make this available outside of fully commercial arrangements, which could be after a period of time? When does it become fully open? Maybe that's one for the Nimbus project to start with. Would anyone like to take that?
Thanks, David. I think that would actually, I would say that would be something that we would be looking at in Alpha when we work directly with the data owners, and there's definitely scope for that. I think it's something that we would encourage. I'm going to also ask Chris to come in on that as to whether you have any thoughts.
Certainly, the direction of travel is for this to potentially form part of a future edition of the network asset risk model, the probability of failure calculations, and I think by that time it would need to be quite well established what the parameters were and what the data sets involved were, so that it was understood by the industry. So as Gaia says, there's a little while to get to that, but that's very much how we foresee this. If it turns out to be a significant improvement like Salem was illustrating, we'd want to make this available and as a standard methodology.
Are there any sensitivities to sharing weather data in particular? It strikes initially from an outsider point of view that it's not the same as having network asset information available, but has that been considered by any of you?
I think on the weather data sets, we're certainly looking at a synthesis of existing public weather data sets. I couldn't speak entirely to a weather data's partners sort of intellectual property rules around a model that gets developed, but I would have thought, given the sort of general operating parameters of this, that I would be surprised if it was not, at least as a technique, freely available, even if it wasn't the specific data was actually had a commercial element to it.
Got it. My question was for the Predict for Resilience. And I think you've touched on it already a little bit, but maybe Joe and Jethro, you could expand to that. So I was asking, how far in advance do you expect to need to be able to make some of these predictions to actually be able to implement any actions within the network? Are you starting to get any feel for that? And are you looking at
absolutely. So we presented results, forecasting up to 14 days ahead, which was our initial motivation was, well, weather forecasting has come on to the extent where there's now skill on these horizons. Let's see how far that translates into fault forecasting. Though through engagement with the control room, while there's kind of interest in forecasting on those horizons for just general awareness, they've told us, the decisions they're taking are, around 5 days ahead at the furthest. And even then, it might be a case of, preparing and not changing anything and seeing how the situation evolves as the incoming weather gets closer, and also is then better predicted in shorter horizons. So anything from 1 day ahead to 5 day ahead is where decisions are being made currently. So they're kind of our priority. So speaking from an academic perspective, I think there's still interest in seeing how well we can predict slightly further ahead, and if we can predict further ahead well enough, if there are improvements that can be made in operational practice to benefit from that. I think today's operational practices are based on the weather forecasts that have been available historically. So. And that's the current situation. Joe, do you want to add anything to that?
I guess just, yeah, not too much to add, Jeffrey. I guess the other key sort of innovation really to bear in mind is that move towards a probabilistic framework as well at those timescales as well. There's very little across the energy industry as a whole in using probabilistic in a kind of operational decision-making way, and I think that's where the other key step here as well. Even though we've narrowed in on the 3 to 5 day timescale, we are still looking a little bit further out, but that leap to probabilistic sort of decision making is the key here, I think, as well.
Hey, Alex, could you let me know if you're ready for the presentation in the chat, and we'll take a couple more questions and then move on to you to complete yours in the break. One of the questions that I have for all of you is there's quite clear synergies between your projects, and has there been any discussion between you about how you can actually coordinate tools and approaches in future?
I'm happy to jump in from the Nimbus side. So yes, we've had quite a few conversations. Actually, Vichy, I think you were involved in some of them. So do you want to give a quick summary?
Yes, thanks, Gaia. Absolutely. So thanks, David. That was actually a very important part of our program. Interoperability and scalability of everything that we're doing is absolutely priority. So a part of the prioritization criteria for the use case is to make sure that we're covering specific parts of needs that are not treading on anyone's toes. So if you saw the 3 finalists, one of which was quite similar to Predict for Resilience's goals, and hence why it was deprioritized. And we have had conversations with the asset teams for SPEN specifically to discuss the applicability for Nimbus and its objectives for SPEN, for transmission operators as a whole and DNOs as a whole. So very close coordination and discussions. I myself see a lot of synergies between them, especially around the conversations about making the data available, making the data part of the open data initiative, and as Gaia has mentioned before, aligning that with the Energy Data Task Force and the Digitalisation Task Force objectives of Ofgem and UKRI as a whole. I hope that sufficiently answers your question, David.
Yeah, great, thanks, Vichy. And one final question, and then I'll come over to you, Alex. Is the land topography, this is from Matthew again, taken into account in the weather-related predictive analysis? And the reason this is asked because the transmission or distribution line running in close proximity to, say, a forestry commission area is likely to have a greater probability of faulting of assets than somewhere near the coast or, yeah, in different environmental areas. Who would like to pick that one up?
I can speak to that one. So there's a couple of points there. One is we are looking at high capacity, sort of 400, 132 kilovolt lines. They tend to be clear of trees. So I'm not sure about the forestry part of things, but certainly topography is part of the data set. We will be looking at both the weather modeling itself should be at a sufficient spatial, should include topographical elements in its interpolation. That's part of the analysis that we would expect to be done. But we'll also be looking at the GIS positioning and direction of the lines, for instance, between the towers as they move through that 60-kilometre area. So there are some going up hillsides, there are some on the lee sides of valleys, that sort of thing. And we'll be taking that into account on a tower-by-tower basis as we move into the analysis.
I think from a Predict for Resilience perspective, this is one of the topics we've picked up in discovery via the engagement as well. Is there's a keen activity that in alpha phase we need to look at suitable satellite imageries or other types of vegetation surveys Spain currently doing within their business to incorporate those data into the forecast. And certainly that's a key point, that when you are in close vicinity to vegetation, then you would obviously have a higher risk of being exposed to debris wind related faults. Jethro, I'm not sure if you want to add anything.
No, not right now. Thanks.
Great. Right. Thank you all very much. Alex, are you available if I bring up the Eye in the Sky slides, and we'll be able to complete your presentation before the break? But thank you all very much for stepping in and dealing with timing issues there from the Predict for Resilience and Nimbus projects. Over to you, Alex.
David, I don't think that Alex is with us at the moment.
Okay, right. We'll call the break there, and hopefully we might be able to squeeze in the Eye in the Sky project before.
I just wonder if David experiencing some connectivity issues there. So yeah, it feels like break time.
Yeah, let's take 10 minutes now, and let's all come back at around 10:20.
Thank you all.